Welcome. Today we will be taking a look at the notes worksheet entitled Vector Applications. And this lesson represents an opportunity for us to reinforce some of the mathematics we developed yesterday dealing with vectors. So we'll go ahead and develop a few strategies and just look at a couple problems together and see if we can get some good reinforcement on that and some good practice. So anyway, let's go ahead and jump right in here. There are just a couple strategies dealing with vector problems. And it's interesting to note there, the number one that I see in your paper, a lot of these diagrams that you're going to draw will create either a non-right triangle or a right triangle. And so if you look at that and you start to see some information form in that triangle that allows you to do law of cosines, law of sines, or right triangle trigonometry, then please do so. I think that's a great strategy. So start looking for your, if you remember the non-right triangle stuff particularly, AAS, ASA, SAS, and SSS, if you see that stuff form, then you don't have to really deal with the concept of vectors. You can really kind of deal with it as sides of a triangle. So just kind of throwing that out there. What I will probably do is really the number two. We were kind of talking about it in terms of the context of vectors. So I will really try to just go back and look at the mathematics from yesterday's lesson and really perform that. So I'll read number two, and that's the way I'll go ahead and progress. So it says change the vectors from magnitude direction form to AI plus BJ. So if we have the magnitude and we have the theta, the direction, then we can get A and we can get B. And when we have A and B, we can add vectors together and get what is called the resultant. Once we have the resultant vector, from there, everybody, we have the math that we developed yesterday to go back and get the magnitude of it and back and get the theta of it. And so that's exactly what we'll do. All right, so I have two examples that we will take a look at here today. The example one I don't think would allow us to do any non-right triangle trig or right triangle trig for that matter, regardless. So this is a good opportunity for us to put it all together with vectors. But the second one, if you happen to see some non-right triangle trig form, please feel free to do it. Okay, well I'm going to read example one and then we'll get started. Three forces with magnitudes of 75 pounds, 40 pounds, and 60 pounds act on an object at angles of, and unfortunately they're written as bearings here, so 60 degrees east of south, 45 degrees east of north, and 30 degrees west of north, respectively. Find the direction and magnitude of the resultant of these forces. So I'm going to do just a drawing down here, just kind of put it together on my board, and then probably have to do all of my math over here. I would encourage you to try to be visual with this as well, give you a good sense of what to do initially, and then we'll go ahead and convert, do the resultant, and come up with our answers. Okay, so I just have a little coordinate plane there. I think that should be satisfactory. It doesn't have to be perfect. And let's just be a little careful on this piece. I've got the three magnitudes and the three directions. Let's go ahead and make sure we get this together. So the first one I see is a magnitude of 75 pounds. And by the way, I'm going to go everything from the origin. That's just the way I'm going to start drawing this out. So 75 pounds, 60 degrees east of south. So let's start off our south axis here in an easterly direction and would look maybe something like that. Okay, good. I'm going to hold off labeling things until after all three are drawn, but I will try to draw them at least somewhat to scale. All right, so there's our first from here to here. Second one, 40 pounds, and here's the bearing, 45 degrees east of north. So off the north axis, go 45 degrees for me. And let's go ahead and do 40 pounds, so it's definitely smaller than that one. I'll go from about there to there. So that would be the secondary vector. Now the third one here, 60 pounds, and this one is 30 degrees west of north. So let's start off the north axis and go west, 30 degrees. And it's going to be in between the first two in terms of the magnitude there. So bigger than this one, smaller than that one. Again, doesn't have to be perfect, but something like that would do. All right. Well, very good. Let's go ahead and start labeling our magnitudes. This one was 75. This one was 40. And this one up here was 60. All right, so 3 magnitudes, all looking great. The key, in my opinion, for this entire problem is making sure you have your thetas correct. So we have to be careful. These 3 directions were given as bearings, but in terms of working with vectors, that theta is not a bearing, it is the angle in standard position. So from here, the easiest thing to do is go counterclockwise to here, or to here, or to here. So let's go ahead and put this together, make sure we get our 3 thetas correct. So the first one, in this case, if that bearing was 45 degrees, what I'm seeing here from east of north, 45 degrees, then this is also 45 degrees. So that one's not too bad, I believe. So from there to there, 45 degrees, that's our theta, good to go. Now what I need you to do is see if you can come up with a theta from here to here. And so in this case, it looks like that bearing was 30 degrees west of north, but what would be the theta going from there to there? I'm seeing this as 90 plus the 30, so tough for me to kind of draw this in here, but I'm going to go from there to there. That should be 120 degrees. So again, we wouldn't use this when we start dealing with our math on the vectors. We use 120 degrees here. Okay. Now I also see a couple different ways to represent this next theta. If I talk about just my primary angle, that would be from here all the way to there. And I can do that. That's not a problem. Let's see. This would be 270 degrees from there to there. And then it looks like the bearing told us to rotate another 60 off that south axis. So I'm seeing that angle in primary position there as 330 degrees. And I'm going to label that in there. I don't have too much of a problem with that. If you don't like that, if it's getting a little too convoluted, theoretically, I'm not going to write it in because I don't want too much in the diagram, but theoretically, could I have just gone clockwise from here to here? And would this maybe have been a negative 30 degrees? Yeah. And the good news is, of course, all the trig ratios on 330 degrees are the same as the trig ratios on negative 30 degrees, of course. And so you can use negative 30 degrees for this last one right here that's in play. Well, regardless, I have 3 thetas. I'm going to go ahead and use those for right now and kind of leave it. All right, so I'm going to go ahead and just do 3 different vectors here. So the first one, I guess that's the 75, and that bearing right there, I'm going to call vector V. And everybody, what we're going to have to do is convert that from using the magnitude and direction. We're going to have to convert that to AI plus BJ. So just a good refresher from yesterday. And so everybody, it's going to be 75, and it's cosine of 330 I. Now remember, if you wanted to, you could use negative 30 degrees here. It works out in an identical fashion. And then plus 75 sine 330J. I'm going to put a little equals on the back there, and we'll get that piece momentarily. Now the second vector, that would be the 40 pounds and this bearing right here. So that's this vector right here. We need the A and the B. We need AI plus BJ form on that as well. I'm just going to call that vector U, if that's all right with you. Call it whatever you'd like, of course. And again, nice and straightforward, everyone. It's magnitude cosine of theta. So there's your magnitude cosine of theta I and magnitude sine of theta and J. We'll get that answer momentarily as well. And then what we're going to do is need the horizontal and vertical components of the third vector that's written there. That looks like that one had the magnitude of 60 and the theta of 120. So again, just if you don't mind, I'm going to call that vector W. What the heck? And let's see, I'm going to have 60 cosine 120 I, and then 60 sine 120 J. Now, it just so happens that you happen to know all these values over the course of our semester from unit circle and working beyond, of course. You know the exact value of cosine of 330. You know the exact value of cosine of 45 degrees, and so forth. We're going to let the calculator do our work for us, but it should be noted if we wanted the precise values, we know them from here. But for right now, I'm going to let the calculator do it. And let's get each one of those into our AI and BJ. So that was our first step. And so let's go ahead and make sure we're able to kind of do that piece. I'm going to go to 2 decimal places on each. So the first one. And by the way, just make sure you're in the right mode, degree mode. So 75 cosine 330. And then 75 sine 330. Okay, and so that'll be the horizontal, and that'll be the vertical right there. Okay, very good. And so let's see, I have 64.95i and then minus 37.5j. So that's what we got from this one. And remember what that tells us. This vector with the magnitude of 75 and the direction of 330 is made up of the horizontal piece and the vertical piece. Horizontally, we're going over about 64.95 and down about 37.5. Okay, good. Let's repeat, everybody. I'm going to, again, bring my calculator on up and do the next one. So this would be 40 cosine 45. Oops, make sure I type that in correctly. And hit enter on that. Good. And then how about 40 and then the sine of 45 degrees? Same thing, everyone. Good. And we knew that probably would be the case. So 28.28 on each. Write that in there if you would. And that would be the horizontal and vertical component of that second vector. So over about 22.28, up about 28.28. Absolutely great. Now the third one, of course, let's get that one taken care of on that 60 and the 120. So here we go, 60 cosine 120 degrees. And I think we saw that coming. And then 60 and then sine 120 degrees. So please make sure you're typing in with me and getting everything. But it looks like it's negative 30 and then 51.96. So negative 30i and 51.96j. All right, how's that look? And again, just in terms of our math here, 30 to the left, 51.96 up for that vector right there. Each vector is made up of those parts. Okay, now we are ready. So we have to go ahead and add them. V plus U plus W. And we add all of these together, add the horizontals, and then add the verticals. And that will basically give us what would be the resultant. Notice I didn't try to draw the resultant in here. I probably could have added one on top of the other and top of the other and maybe have seen it. But I'm going to wait and see what happens with our math here. So everyone, let's go ahead and add those together. I'm going to go ahead and grab my calculator as well. Again, combine like terms at this stage to get the resultant vector. And so let's see what we have going on the horizontals. 64.95 plus the 28.28 and then minus the 30. And so we get about 63.23. So I'm going to write that in there lest I forget. So 63.23i. Excellent. So we are going, in this case, adding them all together. That's 63.23 just horizontally. That's fine. Let's go ahead and get the vertical and see what we end up getting here. So I have negative 37.5 for the first one. Everyone, the 28.28. And then the third one here, 51.96. And I'll hit enter on that, and we get about 42.74. Okay, so let me get that in. Perfect. Now, if I had to kind of draw this, what this is basically saying is about 63.23 horizontally and about 42.74 vertically. So, you know, something up here, give or take. I don't want to go ahead and draw it in really, just not sure about it entirely, but something like this probably would do. And that would be it. That would be the resultant of those three. That would be V plus U plus W. I'm guessing at this stage. I'm just kind of speculating a little bit there. But now that we have that, though, I can get the magnitude. I can get the force, well, the combined force from the three vectors. So the magnitude of our resultant, and then what would be the direction of our resultant. Okay, so let's go ahead and do that, everyone. So nice and straightforward. Once we have this piece right here, we've added our vectors together. Now we can get the two characteristics from it. And so in this case, all I'm going to do is a squared and b squared underneath that root. So 63.23 squared, 42.74 squared. And that's looking good. I'm going to go ahead and put that in momentarily. Let's go ahead and see what we end up getting there. Yep. So I have, what did we say, 63.23, square that one. 42.74 squared. Got that. I'm going to go ahead and square root it. And we get that right there. So the magnitude of the combined forces there would be about 76.32 pounds. Excellent. And now everybody, I'm looking for theta. And so this was where we left off yesterday, is if I have the horizontal and vertical, they're the two parts of this piece right here. So I have the horizontal here and the vertical here. The ratio that connects those two pieces is definitely tangent. And so let's go ahead and do an inverse tangent on that, and that should give us our angle. So inverse tangent of 42.74 over 63.23. Okay. Very nice. Let's go ahead and see what we end up getting here. Inverse, tangent, exactly those two things, 42.74, and then divided by the 63.23. Get that? And I've got a nice looking answer, about 34.06 degrees. And I'm going to write that in there. Now, if you want to write these as bearings, because again, you should be fluent in the standard position representation of the angle and also the bearing representation. I mean, in fact, I'm going to do this momentarily, but I'm going to go ahead and convert it. If you want to leave it in as your theta here, that's fine. So it looks like I have a couple answer blanks. Might as well go ahead and use them. So 76.32 pounds on that. And then theta equals 34.06 degrees. Or, and then again, I'm going to go ahead and write it as a bearing. If we maybe do a 90 minus, so from here to here, I guess, is the 34 degrees. So the bearing would be coming off the north axis, going east. And I'm just going to do 90 minus there just to see what that is. So 90 minus 34.06. And so we get about 55.94 rotating off the north. So either way, guys, it's totally up to you. I kind of like both, so I'm going to put them in there. And that would be that piece right there. And so you can see the three forces acting together, combined. This would be its magnitude, and this would be the direction of the combination. All right, great. Nice problem. Let's go ahead and do example 2. So it says an airplane is traveling at a speed of 500 miles per hour with a bearing of 60 degrees west of north at a fixed altitude and with a negligible wind velocity. As the airplane reaches a certain point, it encounters a wind blowing with a velocity of 70 miles per hour in the direction of 45 degrees east of north. What are the resultant speed and direction of the airplane? Okay. Let's go ahead and draw it out there. Same kind of deal. And give you a couple different ways to look at this. But let's start with that first one. It has a magnitude. In this case, the velocity is our magnitude. And the bearing will sort of be the direction there. So 60 degrees west of north, 500 miles per hour, something like that would do. Okay, very good. And then the wind is going to blow there for a second. Again, I'm going to do this a couple different ways if it's all right with you. But, you know, just in terms of coming off the origin, the wind is going 70 miles per hour, and there's that 45 degrees east of north again. So much smaller Something like this would do. Okay, and the 45 degrees right in there. And so if I wanted to go ahead and draw the resultant, which I might do, it would be good for us to take this vector right here and add it on top of that one. So I'm going to go ahead and do that. As I said, you can take a vector and really paste it anywhere you'd like. So it might look something like this, and as a result, this would be where the airplane's going to head now, and its speed is going to change, and obviously its direction changes, and that's what we're going to go ahead and find. So it's coming here, the wind is blowing it this way, and so it ends up here. These two added together give us this piece. Nice. And as you can see, just one thing to note, again, I'm not going to take this route, but I know you can. Notice what type of diagram or what type of shape that you get right in here. You get what looks to be a nice looking non-right triangle. And if you can start labeling some things in there, you might be able to pull off law of sines or law of cosines on it. Again, I will leave that to your discretion if you really see it. Otherwise, I'm going to go ahead and just do our vectors. So let's go for it. Knock this out. So the first one we do have to be careful on. I have the magnitude is 500, and its cosine, remember theta has to be in that standard position. So we don't want to put in 60 degrees. A couple different ways you can probably do this, but I'm seeing 90 degrees from there to there, and then another 60 degrees from there to there. So when I see 60 degrees west of north, what I'm really seeing is a theta of 150. So please just be careful on that piece. Obviously, if you get the theta wrong, then everything else is going to be for knots because you won't get it right. So let me put the I right in there. So 50 cosine of 150 degrees I, and the 500, and then sine 150 degrees J. Okay. Now I'm going to leave a little room. I'm probably going to have to do that below. I'm going to go ahead and get my second one. I'll just call it W there. And that second one, it looks like 70 is the magnitude. And no matter how you do it there, just in terms of standard position, it looks like that angle is 45 degrees as well. So cosine 45 degrees I, and then everybody, this should be a little more automatic for you, sine 45 degrees and J. And if we're going to talk about the resultant magnitude and direction, what we have to do is actually write a vector for that resultant. So we have to find out what is V plus W. So let's go ahead and do this. I'm going to go ahead and kind of just put a little equals underneath each. Let's go ahead and get this from the calculator and this from the calculator. Again, we know those values. We can keep it in exact form. I think it just benefits us to go ahead and use the calculator, so when we add them together, it's pretty straightforward. So I have 500 cosine 150, and then I have 500 sine 150. And this one shouldn't come as a shock. There we go, because sine of 150 is 1/2, of course. So that first one there, I get negative 433.01, and that's I, and then 250J. All right, now the secondary one, let's get that taken care of. Bring that on up. So second one, everyone, let's go for it with me. 70 cosine 45, and looks like round up there about 49.5 on that. And you should see, of course, we're going to get the same answer here, because again, sine and cosine of 45 degrees is the same. Nice. So breaking each one down into the horizontal and vertical components, so I have 49.5 I and 49.5 J. Absolutely perfect. Now what we want to do is add those two together, combine the like terms, horizontals together, and then verticals together, and we should be able to get V plus W. So let's get those two pieces. I'm going to go ahead and keep working with my calculator and bring up all those numbers. So negative 433.01, and let's see, plus 49.5. Get that one, so that's going to be our vertical component on the resultant. And then how about the 250 and the 49.5 on that, and this should be the vertical component. Okay, so let's get those. So negative 383.51 I's, I think is what I saw there. And then I believe a 299.5 J. Absolutely perfect. Good, so now I have an algebraic representation of this vector right here, from here to here. Its magnitude will represent the velocity after the wind has had an impact, and the theta will represent the new direction there. All right, perfect. Now, actually, I'm thinking of one thing, not just yet, but I'm curious if you remember one part of this when we do the angle. Magnitude is a piece of cake, so let's go ahead and do that first. And so I get negative 383.51. Going to square that. And then how about the 299.5? Let's square that. All right, so this should give us the new velocity when the wind has had an impact on that. And so let's see, negative, what was that, 383.51. Let's close that and square it. And same thing here, everybody. How about that 299.5? Let's square that as well. Looks good. I'll go ahead and apply the square root on this at this stage. And so notice the wind has slowed it down. And so it slowed it down to 486.6 miles per hour. Absolutely perfect. So the magnitude there is 486.6. And in fact, I'm going to go ahead and put that in here. Just have an answer blank on this worksheet, so I might as well use it. And that is the new speed of the airplane, 486.6. Now here, I'm curious if you remember. It hasn't come up just yet. But let's see if you remember. So of course, I'm going to do an inverse tangent. I have the B and the A, the vertical and the horizontal. So I am going to do inverse tangent of 299.5 over negative 383.51. Okay, now I'm going to do it on the calculator. I know what's coming here. I'm curious if you can see ahead a little bit. Watch what happens when I do an inverse tangent on this, and tell me what went wrong, actually. So 299.5 divided by negative 383.51. I hit that, and I get about negative 37.99 degrees. So here's what that would look like, everyone. Negative 37.9, whatever it was, degrees. That's actually a clockwise rotation just about here. Wait a minute. What happened? Hey, guys, what do I have to remember when the horizontal part is negative? I'm in the wrong spot, and so I have to add 180. So remember, inverse tangent can't give us that second quadrant angle. So as a result, we have to add the 180. There we go. There's the 142. And so that looks like a better angle here. I'm going to write that in. 142 degrees. Excellent. So let's go ahead and put that in 142.01. So we were at, what, about 150 degrees. And now the wind obviously pushed us that way, and so it knocked us down a little further east. So 142. I'm going to go ahead and write this as a bearing. What would it be from here to here? It looks like if I take this and I subtract 90, I'm going to get it. So I'm going to go north, and that seems to be about, what are we looking at there, 52.01? There we go. Again, just two different ways. So we saw it as a bearing. Originally it was 60 degrees west of north, but with that wind blowing in the direction it is, now it changed it. All right. Good. All right, everyone. Just obviously you're going to get some practice on this individually and also with a partner, but you can kind of see that math starts to, the same type of math starts to come back again and again. All right. Please let me know if you have some questions. Thanks for listening.